Okay, hi everyone. This video is going to be all about covalent bonds. So we're going to talk about their properties, something called diatomic and polyatomic molecules, and then we're also going to talk about covalent nomenclature. Remember, that's in naming rules for covalent compounds. Okay, so first of all, covalent compounds form distinct molecules, meaning atoms that are chemically bonded to one another. This is in contrast to ionic compounds that form those 3D crystal lattices that can really vary in size a lot. But with covalent compounds, they have a distinct ending and stopping point versus the ionic compounds. Covalent bonds between atoms are also strong and they are hard to break. However, covalent compounds have low melting and boiling points. This is because the attractive forces between the different molecules are weak. Okay, they're not bonded, they don't have that ionic attraction between them. So we have a weak attraction, so it doesn't take a lot of energy to overcome these attractions and actually separate out these different molecules. As a result, covalent compounds tend to be liquids and gases at room temperature. Covalent compounds also do not conduct electricity because there's no separation of charges, and with no separation of charges, electricity cannot flow. They also tend not to dissolve well in water, which we'll discuss more when we talk about polarity later this year. Okay, so let's do a quick review. Looking at these chemical formulas, are these compounds ionic or covalent? So remember, we want to think about whether they have metals or nonmetals in them or a combination of the both, two of them. So go ahead, pause the video, try and think through what these would be, and then go ahead and hit play when you're ready to check your answers. Okay, so the first one, lithium and fluorine. Well, lithium is a metal. Fluorine is a nonmetal, so that one will be ionic. Sodium and iodine, same thing, metal, nonmetal, so that one will also be ionic. Carbon and hydrogen. So carbon is a nonmetal, and remember, hydrogen is also a nonmetal, even though it's on the left. So this one only has nonmetals, so it will be covalent. Okay, the next one, sodium hydroxide. So this one's actually a little bit tricky, and it's both ionic and covalent, okay, because we have metals and we have nonmetals. Well, between the sodium and the hydroxide, we have an ionic bond, but between the O and the H of the hydroxide, that's actually a covalent bond in there. But overall, we tend to think about it with ionic naming rules because it does have that present. HCl. Okay, so we have two nonmetals. That one's going to act more like a covalent compound. And then H2O, which we know as water, that is also covalent. If you have any questions on these, please go ahead and let me know. But otherwise, let's move on. Okay, so we have diatomic and polyatomic molecules. Well, if we think about the word diatomic, di meaning two, atom, referring to the atomic. So these are two atom molecules. And what makes these special is these two atoms are of the same element. And they contain the elements hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. These elements, unless they're bonded with something else, a different element, will always pair up with a twin. Okay, so the way that I always remember this is the Honkelbrief family. Okay, I know that sounds kind of funny, but the Honkelbrief family, these always have twins. So they're never just an H by itself. It would always be hydrogen with another hydrogen or hydrogen bonded to something else. We also have polyatomic molecules. So poly meaning many, so these are many atom molecules that all have the same element. So some examples of this are phosphorus, which finds groups of 4 phosphorus atoms grouped together, and sulfur, which has 8 sulfur atoms grouped together. So make sure you remember these, keep these in mind. They will pop up later this year, so you do need to know them. Okay, so if we look, here's just a quick picture showing them and kind of where we see these atoms the most. That first row of all those atoms bonded together, that is going to be the diatomics, and then down below we have the polyatomic atoms. Okay, so thinking about metals and nonmetals versus nonmetals bonded to nonmetals. So on the left, we have ionic compounds. On the right, we have the covalent, or also known as molecular compounds. So if we look at these, what are some similarities between the two types of naming? And what are some differences? So go ahead, pause the video, think, look for these for a few seconds, and then I'm going to go ahead and talk about them. Okay, so first for the similarities, you will see that the first element name is still the element name, whether it's for the ionic or the covalent. So we have calcium, iron, sodium, sulfur, nitrogen. We're not changing that name, whether it's ionic or covalent. The other thing is that IDE ending that we use for the monatomic ions, or in this case, the monatomic elements for covalent. So we end in "ide" for both the ionic and covalent. The only exception is for those polyatomic ions, we have whatever their ending is. So for some differences, in the ionic compounds, we have Roman numerals for the transition metals, plus remember there's extra special ones like tin and lead that also like to have Roman numerals. And for covalent, we have those prefixes. So we have the hexa, the di, the pent. Those are all talking about the number of atoms that we have, which we don't see with ionic compounds. Okay, so let's actually go over the naming rules for covalent compounds. The first thing, for the first element, you start with the element's name. You just write out whatever it is. For the second element, we're going to start with the "ide" form of that name. So remember, we take off the ending and we add IDE. Then we're going to use prefixes to show how many atoms of each type there are, and I'll show those prefixes in a second. The other two rules. We do not use mono on the first element. So if we have one of that element, we just write the element name. If we have two or more elements of that first element, then we do need to go ahead and use the prefix. And also, if we have any cases where we have AO or OO that come together with using the prefix and the element name, we're going to replace it with just the letter O. Okay, so the covalent compound prefixes are the Greek prefixes that we see below. So 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So you've probably seen these prefixes before with other things like hexagons or decades or triangles, things like that. So they're pretty familiar. Just make sure that you do remember what they all stand for. So as I said, if we have that AO or OO combination, we're going to replace it with just a plain old O. So this is showing how this works with the element oxygen, which is oxide, if it's the second element. So we have monoxide, so the OO there goes to just a single O. Dioxide, that is okay. IOs are okay. We can keep them as they are. So dioxide and trioxide don't get changed. Tetroxide, we get rid of the A and just leave the O. Same thing with the pentoxide and the hexoxide and the heptoxide. For oxide, we get rid of that extra O and it's just one. And then for the nona, again, we get rid of the A, so it's nonoxide, and then same thing with the decoxide. So if you have any questions about how to combine those, please let me know, but otherwise reference this list. Okay, so let's work through some examples. So we have N2O3. Okay, so we think about those rules. We're going to go ahead and use rules 1, 2, and 3 for this one. So N stands for nitrogen, O stands for oxygen, which becomes oxide. And then we're going to go ahead and add those prefixes. So we have 2 nitrogen, so that's going to be dinitrogen, and then 3 oxygen will be trioxide. So all together, dinitrogen trioxide. Okay, this next one is also going to use rules 1, 2, and 3. So we have 4 phosphorus and 10 sulfur. So if we put all this together, we have tetraphosphorus. Remember, we keep the phosphorus name as it is. And then we have decasulfide. Okay, tetraphosphorus decasulfide. Okay, the next one, CF4. In this case, we only have 1 carbon atom. And since it's the first one, we're not going to use that prefix mono. So that's going to be rule 4 that we add to our list. So this one is just simply carbon tetrafluoride. Again, we do not use mono on the first element, only on the second one if needed. And the next one, PCl5. Okay, so we have the same case again where we have one of the first element, but we're not going to use that mono, so this is going to be phosphorus pentachloride. Okay, so for this one, we have 2 chlorine, so we will use a different prefix for this. We're going to use di for the chlorine, and we have 7 oxygen. So this is going to be a case where we have an A and an O next to each other because the prefix for 7, hepta, and oxide would have an A and an O. So we're just going to replace that with an O. So this one ends up being dichlorine heptoxide. Okay, so for this one, we have that A next to the O again. So we're going to have rules 1, 2, 3, and 5. So we're going to have tetra for the phosphorus, so tetraphosphorus, and then hexoxide. Remember, when we have an A and an O, we get rid of it. Okay, this next one is my favorite example because it actually combines all of the rules into one case. Okay, so we have 1 carbon atom and we do not use the prefix mono for the first element. So that's rule 4. And then for number 5, we have mono, which ends in O, and we have oxide. So we're going to replace that double O, which is just single O. So carbon monoxide. Okay, so I hope that helps. Please let me know if you have any questions on covalent compounds, and I will see you all later. Bye.